Yeah, thanks. So I want to start by reminding us of a great theorem of Thomason, which, loosely speaking says K-theory is invariant under derived equivalences. So slightly more precisely, it says if you have, say, exact categories with weak equivalences, and well, satisfy some hypothesis, which are okay if you work with pre-triangulated DG categories. Pre-triangulated DG categories. So I'll say a little bit more about that later. So if you don't know what that means, then it doesn't matter for the moment. The main point is that, so if you, in these situations, if you invert weak equivalences, you get triangulated categories. Well, it's one of the things, triangulated cats. And well, the hypothesis, if that is an equivalent on what's called derived categories, then the associated K-theory spectra are also equivalent. And together with Waldhausen's vibration theorem, that's incredibly powerful to prove lots and lots of theorems in algebraic K-theory. So especially when you're interested in the K-theory of singular varieties, yeah, most computations we can do can rely on that. So because, I mean, there's a whole school which looks at derived categories of algebraic varieties and finds semi-orthogonal decompositions and stuff like that. And all of that you can feed into K-theory and get lots of results. You can compute the quadrics, K-theory of quadrics. You can prove blow-up formulas and all these things that are in that you need to know about when you study singular varieties. Anyway, and of course the question is, how about Hermitian K-theory or GW theory? Is there a similar theorem that is true? And I'll start with an example, in fact a counterexample. Let me explain that, which will explain why we need extra hypotheses. So I'm going to introduce the notation. So R is going to be, well, let me call it K. I like to call it K, but it's going to be a commutative ring for the moment. Just okay, and I will denote by C index K the category, just the category of bounded complexes of finitely generated projective R modules, or K modules, would stick R. And I'm going to stick an N here to indicate that I'm talking about the duality that goes into the nth shifted module K, so placed in homological, well, I guess, cohomological degree minus m. And okay, so this is a category with duality. If I put the canonical W amplification here, it's a category with duality. And I can equip that with various weak equivalences. But actually it fits, it's for instance also a DG category, pre-triangulated. So now if you look at the category of functors, so that's just from, well, this category, so we'll be looking at the category of morphisms in this category of bounded chain complexes. So this is just a category of morphisms, right? So and whenever I have a morphism of chain complexes, I can take the cone and you get another chain complex. But if you still make it precise, then the cone changes to duality, and you have an extra one here. Now, here we, of course, have quasi-isomorphisms, the usual quasi-isomorphisms, actually, or chain homotopy equivalences in this case, as weak equivalences. And here I'm going to put weak equivalences precisely the pre-images of those. So that's the pre-image of, so everything here is going to be, by definition, an weak equivalence if it's under the cone, a quasi-isomorphism. And it's easy to check that actually this is so inverting weak equivalences, this becomes an equivalence of trying categories. So it becomes an equivalence after inverting weak equivalences. This is an easy exercise because you have a section and then you just. So Thomason's theorem applies to say that they have the same K-theory. Anyone looks puzzled? Anyway, so now how about, so we can look at what happens now on the level of Grothendieck groups. So, okay, let's look. And that's all very explicit. And I'm just going to stick now here to the Grothendieck group where n is -1, because then I know what the right-hand side is. So this is C0, K, with quasi-isomorphism. And I told you yesterday that this is just the usual Grothendieck group in degree 0, let's say, of just the ring K. Okay, and here I get a map. And I claim that if K has a residue field of characteristic 2, this map is not surjective. So that's, how do we do that? Well, so when you, oh, the n is a -1, thank you. Yes, I apply this to n equals -1. Yep. If you study what happens under this map, so let's just look, so I claim this is not surjective. So I mean, I have a surjective map, just take the rank mod 2, right? So then I get Z mod 2. So I take duality, so yeah. I mean, I've told you what. At this point, well, you mean it's not, if K is a ring which is connected, then that I'm okay. But yeah, take a local ring if you want. I'm going to pass to, yeah. In a moment I'm going to, because all of this, choose a, well, anyway, let's look at what happens here. So if you take a space here, and you analyze where it goes to something, so up to hyperbolics, to something that has some space of some dimension. Let's assume, well, okay, let's say K is local, let's say. But really, I mean, you can, you have this diagram and you choose a residue field and then you go to the local ring. And then this goes to something with Gram matrix. 0 is over here. And then, well, it's symmetric, so it's going to be something Aij here and then Aji here. So if you study what that map does. And the problem is that if n, so this is this n here now, not this, let me call it m, is odd, such a matrix always has determinant, this matrix has determinant in 2 times K. And that means that if K has a residue field of characteristic 2, this thing can never be invertible. And that means we will never ever get anything of rank, of even rank, of odd rank. Why? What is odd? No, I said if.
Why? Why is that 2K? What's the reason?
You just compute I mean, I'll give you another reason in a moment, but you just compute a determinant.
Okay.
You compute a determinant because these are the same things. You rearrange them and see it's twice. But that was the first. The second argument is if K is characteristic too, then of course symmetric is the same as skew symmetric, which is, and if you look, everything on the diagonal is 0, so we're actually symplectic. And we know that symplectic is even dimensional. Okay. But I mean, I wanted to say it this way because you can see that when the characteristic, when 2 is invertible, you can have odd guys here. Okay. So there's no contradiction in this case. So if M odd, this is always, so this means if, so what we see is that if K has a residue field of characteristic 2, that means that this composition is 0. I can't remember, so that rank, cone, that means rank cone is 0. So yeah, so that's what that says. But yeah, I mean, but for instance, I mean that's not the case when. So I mean, for instance, if you look at the easiest example, 1 1 1 1 everywhere here, this the determinant of that is 2. So this gives you actually a non-degenerate space when 2 is invertible, but of course it's not. It does not when you have a residue field of characteristic 2. So upshot, that means that the map here, yeah, that is, yeah. So that means GW is not invariant under derived equivalences if, yeah, so I mean in general, of course, general, if, well, it's not in your whatever category you're looking at. Well, I mean, I started the lectures by giving a definition of Grothendieck space, which is the K-theory of the symmetric monoid category of inner product spaces on some ring. Once I decide that this is what I want to study, then that comes out. You can change the. Well, it depends on what you want. I want to study this symmetric monoid category and its K-theory. Because, well, for instance, the Witt, so I mean, the Witt group or the Grothendieck group that comes up in this situation, for instance, comes up in A1 homotopy theory. So if you want to say anything about that, using that, that's what I want to do. That's okay. I mean, you can give lots and lots of different definitions. I'm not studying the other definition. You can do that. There's lots of work to do.
But could it be that this definition proposed gives you different answers?
Well, I think this definition I propose would obviously be invariant under derived equivalence.
I see.
Well, what I think you can, I think you cannot have both. I think you cannot have both, either vibration and invariance under derived equivalences. So my feeling is you cannot have both. So I explained last time the vibration theorem, which is true without any hypothesis on the residue field or whatever. And my feeling is you cannot have both at the same time. And so you choose which one you want. And, well, at least from algebraic geometry point of view, there's a definition of Knebusch of what the Grothendieck group of a scheme should be, even independent of characteristic. That's the definition I take. Then you get, for instance, a Zariski descent that I explained yesterday with that definition. And that's what that is, okay? And then it's just a feature that, well, okay, it's not in the derived equivalences, so you have to deal with that. Okay.
Can I think about this example the way that means invariant under derived equivalences is the same as asking whether the map from A omega to its derived category is an equivalence in Grothendieck. So this just now resembling the fact that function categories don't come with the derived category.
No, I mean, I told you, well, I'm not understanding quite what the question. This one is a derived equivalence, so Thomason's theorem applies. So they have the same K-theory. And if you just Does that answer your question? I mean, this is an example that is a derived equivalence. And if you compute what happens on Grothendieck groups, that's what happens. Okay, so yeah, I mean, you can change definitions, then you get different theories, and you prove different theorems. But I mean, yeah, I think if you want to study the K-theory of inner product spaces, then that's what comes up. If you want Zariski descent and Knebusch definition, you're sort of stuck with that definition. Okay.
So the fact that the derived categories are clear doesn't see anything about the drive.
I mean, it automatically preserves the dualities, of course, but
Does the category of form have a derived category?
well, you can think about what should be that mean. And so you if you want to make a theorem like that true, say, then you have to define what it means to be a derived equivalence in a much more subtle sense. Presumably there is something, and the test will be if you can use that to prove what's called Nisnevich descent. In K-theory, there you use derived equivalences, and that's something that we don't know in the generality of just schemes over Z for Grothendieck Witt, because that fails. Anyway, so that's why, I mean, if you want that, you have to have this hypothesis in there. So and I mean, yeah, I mean, but yeah, I mean, I mean, anyway, you pick what you want to study, and then you see how far you can go. That's okay. I mean, anyway, yeah, I mean, okay, so now I've explained why we need some extra hypothesis. I mean, I do still think that all the geometric results like the Nisnevich descent will hold in this canon, yes, but you just have to give a more subtle proof. Okay, I mean, yeah. So So now that's why we're going to assume from now on that our base ring has two invertible in here. So to go further and try to make Thomason's theorem true in the world of for Hermitian K-theory. Okay, so that means the context now is going to be some exact category with duality and weak equivalences, and and you need to you need a framework where you can talk about the homotopy category in such a way that it's a triangle category, for instance. And so you pick your world that you want to choose, and I think the simplest world to do that in is the category of DG categories. So I'm going to assume that A is a DG category. Okay. And to make my life simpler in this talk, although this is not necessary, I'm going to assume this is pre-triangulated. I'll recall what that means. Okay, but all examples that I want to apply to are of that form. So and then of course duality and blah blah. So it's going to be a pre-triangle DG category with weak equivalences and duality. So I guess DG category just means category enriched in the category of chain complexes in the closed symmetric model category of chain complexes in K modules. So HOMs are not, I mean, they're just chain complexes now, and composition is compatible with tensor product of chain complexes. Yeah. So that's all I want to say at this point. Yeah, to the G category, you have associated various other categories. This has the same object. The only thing is, so HOMs are now chain complexes, right? We can take degree 0 chain maps. So this is the HOMs in this category are just degree 0 maps in your DG category, and you have HOM in this category. Just you take cohomology or homology of this. So my chain complex is always cohomologically graded, so although it will never come up really. So now, so I say, what's an exact sequence? So a sequence that's of x, y, z is called exact in, I mean, a sequence in your DG category is called exact if, so it's a sequence in the underlying, so this category I call the underlying category, and then your DG world that sits behind is some homotopical data that's there in background. But really, I think of it as such a this is a category, just an ordinary, let's say, K-linear category, and then in the background you have all this homotopical data of chain complexes as HOM. So it's a sequence in the underlying category is called exact if, just if it's exact, actually split exact in the category of degree 0 homomorphisms. So let's reality check. So if A is just chain complexes, let's say, over some ring, whatever, then, well, so this is a DG category, then this is, then a sequence, so, I mean, then Z0, this is the usual category of chain complexes and chain maps. H0 is the usual category of chain maps up to chain homotopy. And a sequence of chain maps, of chain complexes and chain maps is exact if and only if we forget differentials, it's split exact. Okay, so that's what all that says. So, so what does it mean now? A is called pre-triangulated, if two things happen. A is exact, and the functor from A to, we can always take tensor products of DG categories, and that gives you a new DG category. And so I have this category, I mean, that's okay, although this next one doesn't make any sense at the moment. Recall this is the category of bounded chain complexes of projective modules in K. And actually I should take maybe K, well, free modules actually. I defined, did I not say so? Well, sorry, yes, thank you. If that, I give you, explain what an exact sequence is. A is called exact if that A is an exact category with exact sequences that I've defined. Sequences above, yeah. So yeah, for instance, yeah, bounded chain complexes of projective modules is an exact DG category. Okay, and pre-triangle means exact, and so now I have to, well, apology. So I said for, I mean, I actually really, for this definition, I want this to be just to be the free modules. Okay. bounded chain complexes of free modules. And then I require this to be an equivalence of about DG categories. But in fact, you only need to check as an equivalence on the underlying categories. Okay, and so the point is, if A is pre-triangulated, then in a canonical way, its homotopy category is triangulated. And this example is pre-triangulated. That's, well, yeah, I mean, this thing has, well, cones anyway. It has a cylinder, right? And so anything here is a cylinder. And because this thing is exactly required as to be an equivalence, you have cones and cylinders and everything. Yeah, so, and then, of course, then we have our, so this is the DG category part. So then, so for what I do, I only consider weak equivalences to be sort of a set of morphism, sort of set of morphisms that I guess what should I say, a saturated set of morphisms that is defined by taking pre-images of taking homotopy category modulo out some I guess saturated multiplicative set of morphisms, so that this is actually a triangulated category. So, and I only consider weak equivalence, set of weak equivalences. So F to be a weak equivalence if and only if F is an isomorphism here. So that has the effect that when I localize that, this is actually a triangle category, and that's the maps in. So this is a triangulated category, and maps are weak equivalence if and only if the isomorphisms in the drive category. So I only consider sets of weak equivalences of that sort, such that the drive categories are quotient drive categories of the homotopy category. That's the normal thing to do. Anyway, so, and what else? Oh yeah, we of course have the duality, but that's, well. So yeah, and of course the duality is now a functor from A to A up, which is now a DG functor. And can is a natural transformation. So this is, which is a weak equivalence. So it's a closed degree 0 natural transformation, which is a weak equivalence, I guess, for every object. Yeah, that's it. That's the definition of a DG category with weak equivalences. Oh yeah, and of course the canonical W and alpha K. So this always satisfies, as usual, the identity which is automatic if you take hom into some object. Yeah, so now we want to define the Grothendieck spectrum. So I mean, yesterday actually, so I've only defined you the space. One can make this into a spectrum in various ways. But the way I make now, we make GW. So I'm going to define the spectrum now. going to be a spectrum, actually a symmetric spectrum. And so, I mean, in some sense, you want to mimic what you do for S dot construction. So you have your category of Hermitian objects in here. Okay, and then you want to iterate. So, so the subdivision of the S dot construction, which I call R dot, you can do that. So, but it turns out that it's not quite the right thing, because you can prove that this is actually even. So, yeah, I mean, so if you apply R dot to GW, then you don't get a loop. It's just a fact. So, however, and that's sort of an observation, if I tensor, so I denote Cn, we call this so this is now the category of say free bound complex of free K modules with duality in Hom K shifted by N. And so this is going to be, so I'm going to denote that just as a tensor product. Now, if A is a category with duality, DG category with duality, then this thing is also DG category with duality. And since we assume A is pre-triangulated, this cat is actually equivalent to the original category, just has a different duality. Okay. Do I want to know? That is the definition. Just because I don't, yeah. In fact, I sometimes actually just write that. That helps. It's even shorter. Yeah, so anyway, so that's so all we do is we just change the duality here. So here's the original duality, here's a duality shifted by 1, essentially. And then we take the next one, iterate, and change the duality. So, and so as a symmetric spectrum, of course, you have the, well, yeah, I mean, Sn acting here, which interchanges, so this is, so that's not what I want. And that's not what I've written. So this actually, this is equivalent to what I'm writing, because I want to really strictly sort of like, I need to have some tensor products here. Okay. Which is equivalent, so it's, I mean, there's an equivalence. But under this equivalence, you don't really, so here you see the action of the symmetric group. So here you see the action, and you don't really see it on the right hand side. So, yeah, so this becomes a symmetric sequence. And so I need to tell you the bonding map. The bonding map, in order to construct it, requires a theorem that I prove, which is that if we take pi 1 of this, actually, let's say pi 1 of the first space, that is actually isomorphic to the Grothendieck-Witt group. Well, that's true for A. Let me just write it for K of K in degree 0. So that's a theorem. And so here you have a canonical element, and so which under this isomorphism corresponds to something here. And then it's set up in such a way that you can, well, this is actually a module over so R dot CK, blah blah, the way it's defined. And so that means you can cap with the element that I've defined there, and that gives a spectrum. Okay.
So as written, it's symmetric sequence of categories, or
I never realized unless someone watches. Yeah. So
it's just categories.
yeah, but I mean, yeah. So if since you ask, you take the realization, you have topological spaces, and then you get bonding maps, and then. Yeah. Okay, so this gives a spectrum, and the theorem is that this is a positive omega spectrum. But it all uses that you were working over 1/2. I mean, even this one, Theorem, uses that. GWA, that's just written down here, is a positive omega spectrum, representing precisely what we did last time. So, such that, well, it's infinite loop space is the space that I've defined last time of an exact category. So Z0 is now an exact category with duality and weak equivalences. And so this is what I've written down, defined yesterday, as the homotopy fiber from R dot to S dot. And yeah, so that's what it is. Well, here, this isn't. Oh, you're looking at this. Yeah. Yeah. That's right. That's right. So yeah. So that's right. So you can think of it in two ways, and give equivalent ways. You can take the underlying category here and then take R dot, which I have defined yesterday, or you do all of this in a DG world. Then what you get, that's actually what you should do. Then you get a DG category, blah blah, simplicial DG category with weak equivalences, and then you take the and I forgot the omegas everywhere, the weak equivalences. Now, the weak equivalences by definition are all degree 0 maps. So this is now just an ordinary just category with duality, and then take the Hermitian object from there. That gives us an equivalent spectrum. Yeah. Okay. So yeah. Okay. So that means we have generalized, at least under the assumption to invertible, what we've done before. We get a spectrum, and now out pops so if you compute the negative homotopy groups for the S dot construction, if you do that, you don't introduce any negative homotopy groups. Here you do. So let me continue. So yeah, I mean, of course, the homotopy groups of the spectrum are the groups GI. Now I've defined GI, even when I is not positive, or yeah, can be negative now. So what is that? Well, if I is negative, when I is positive, I told you what it is essentially, because I said it's the last thing as last time. Well, it's been several years ago. So, but if it's negative, then in fact what you get is, well, the derived category of A is a triangle category with duality, and then Obama has defined Witt groups of such things, and that's what you get. So actually in negative degrees, the spectrum has negative homotopy groups in general, non-zero, for periodic, going down all the way. They're being they're the Witt groups. Or you may call them L groups, if you wish. So what else? That's right. Let's do that. Yes. In this case, you don't get negative ones. And okay, so if you take A op, A cross A op, where A is some exact category with DG category with weak equivalences. I mean, yeah, with all the decorations here, then that's just that's K-theory of A. Connective. Okay, no negative homotopy group. So that means you need to think of this spectrum that I've just defined as the analog of connective K-theory, even though it's not connective, but that's the correct analog.
There is no
Yes, no, what? Basel one, yeah.
But you also have this L theory, channel splitting, which relates the L theory of RZ to L and then copy, shifted copy. This is one reason how you define.
I'll get to something like that in a
But this will be confusing because now this can't really be the case.
well, but this is because, I mean, you don't have the Basel one for connective K-theory. You just to take.
That's the point, but you have negative
Exactly.
here, and you would expect that you have a channel splitting, but you probably can't have it.
Well,
Second line.
anyway, so, well, there's a difference. So this is the analog of connective K-theory. There will be an analog of non-connective K-theory. Yeah. But people get confused that the connective version of GW is actually not connective. And that's what it is. It has negative groups, the L groups, Witt groups. Okay, so that's. And so maybe it's not. I don't know what to call it. It's not connective GW. It's the but this is very useful because you understand what happens in negative degree. Whereas for the sort of the other version, it's the analog of the non-connective K-theory. You don't really understand what's going on. Okay, what else? Yes, and so now we have done everything such that if I have a map of DG categories with weak occurrences, always under the assumption 2 invertible, such that on the derived categories you obtain an equivalence, then indeed you have an occurrence of corresponding Grothendieck spectra. So that's the theme, the analog of Thomason's theme that we were after, and we needed to. That's yes. From now on, everything. It's still. I'm still. It's just one theme, all in one go. So, yeah. So if you want, I mean, it's to stress it. But everything that I've written here is. Because I gave you a counterexample before. Yeah, and then together with the vibration theorem, if you have a sequence of DG categories with weak occurrences, again under this hypothesis, such that the on drive categories you get an exact sequence of triangulated categories, by which I mean this is a full triangle subcategory of that closed under direct factors, and this is the log quotient of that by that. Okay, then you have a long then the associated sequence of Grothendieck space with spectra now with the L groups in negative degree, and that actually is forced upon us by this property. It's a homotopy formation. Okay, so so in this sense, everything is as nice as in K-theory under the hypothesis 2 invertible. And let me give you one example of an application of that, which was actually the beginning of the investigation for me, why I wanted to set it up all the way I did it.
Out of curiosity, in this statement before you erase it, can we get rid of the word positive if we add some conditions on A, some kind of group-like condition on A?
Well, I mean, in the degree 0 part, I just put in the category of Hermitian spaces, okay, which is like if you just take a ring or something, it's just, I mean, it's not group complete. So, but the reason is because you want a multiplicative structure. You want it all so that when you have a, I mean, there's a natural, it's the way it's set up that if you have a DG category, you have natural map from GW of A, wedge, GW, not wedge, I mean smash, GW of some second category, to the GW of the tensor product of the DG categories. There's another reason why we take DG categories, because it makes sense to take tensor products of DG categories. Okay, and it's associative, and so you can get products easily out of all of that. And that's why we and that forces us to have a space like that here.
Oh,
You
so
see.
there's no reasonable condition on A where
No.
you get rid of positive.
No. So I wanted to explain one consequence of that. Here's the example which led to the counterexample at the beginning, and which was the beginning of the investigation of the whole thing anyway. So remember we looked at the category of morphisms in A, and so I use now my notation, so I take the nth shifted duality here, and I have this cone, okay, which goes to A n plus 1. Okay, if I have weak equivalences, now I use the weak equivalences induced by that, not the ones that forces it to be in equivalence, but the ones that come from A. And then I have the canonical map from AN in here, which just sends an object A to the identity. Okay, so a sequence, and it's also easy to check that this becomes exact on taking derived categories. Okay, so that means we get a vibration, and so I'm going to introduce. So I use the notation GW upper n to indicate GW of A n. So n with the A with the nth shifted duality. So that means you get a vibration. So I'm not even writing A now anymore. Well, maybe I should here. This is n of the functor category, but I'm not going to write the weak equivalences unless I have to. GW n plus 1 A. So, and then from this vibration theorem, or what I've written down there, this is the homotopy vibration. And well, there's various things to say about it. First of all, you can actually determine what is the next map. This is coupled with a certain element, where eta is an element in your ground ring GW minus 1 of K, which is, well, by the identification of negative ones, is just the Witt group of K. And so you have, again, 1 in here and an eta here, which corresponds to here. So we take that. And so this is also by additivity. This is just K-theory. Okay. And then you have a forgetful functor, hyperbolic functor, and that's an exact triangle, what's it called, triangle in the homotopy category of spectra. So, and because it realizes to the usual bot sequence in topology for KO, I call it bot sequence. Okay. And so, well, so classically, there's definitions that KO we made. So let me introduce another notation. I'm going to write GW epsilon. Well, you have always the canonical W identification by if you change the W identification to epsilon can. Okay. So epsilon is plus minus 1. So always the same. I haven't changed any of the assumptions. It's 1/2. I mean, all the G cut is over 1/2. Because I mean, maybe you can make some statements more general, but I'm not going to bother for the moment. So anyway, so yeah, so now Covey makes a definition that this is the homotopy fiber of the forgetful map. So V stands for forgis. Should be easy to remember. So forgis. Okay. Now, and U. So this is by what I've written here. I guess this is the forgis to 0 case, I guess. Where if this is the forgetful functor is here, when n is 0, you get the loop of GW1 of the same sign epsilon here. And U classically is defined as the homotopy fiber of the hyperbolic map from K-theory to GW. If I don't write any, then I made 0 here. And by the Bott sequence, this is just, so we take the hyperbolic map, which is here. This is for where n is 0, so this is GW minus 1 epsilon. And now it's easy to see, and there's a for periodicity in the upper index n, so GW n epsilon is the same as GW minus epsilon n plus 2, simply because you can multiply by k1 this non-degenerate form, which is skew symmetric. So multiplication has values in k2, but it's skew symmetric because we're talking about chain complexes. So if we cap with that, you find an equivalence, and so I can change this into omega epsilon minus epsilon here. Do I want to do that, or which one do I want to change? Let me write this is GW upper 1 minus epsilon. And so what you get out of this is the formula that V minus V epsilon is the same as loops of U changing epsilon. And that's, Karubi's equal to fundamental theorem, now in the generality of DG categories, and independent proof of what Karubi did some time ago. Yeah. K-theory is actually still connected here. Right. It's Morphism. You're right. That's right. That's why you can define, if I invert eta, which I can do, just taking the colimit, I get actually just L theory. Because in negative degrees I don't change anything, but I just add more and more things on top. Yeah, and so in this sense, it's actually not quite Karubi's version, because Karubi uses a different delooping. He doesn't use K. That's right. So let me go to. Say again? Yeah. That's right. That's right. So the analogous statement is true for connective K-theory. Yeah. The statement that says, if you have, let's say, DG cases with weak equivalences, no assumption on characteristic. We have a sequence, where is it? A, B, C, such that this is an exact sequence of triangle categories. Verdier quotient, this is the full subcategory of objects that go to 0. This is the Verdier quotient of that by that. Then you have one multiplication of connective K-theory. No. No, because pi naught, this is the Verdier quotient of that by definition. So every object here comes from here. Well, it's not idempotent complete, because we didn't require this to be idempotent complete. But anyway, so there's the other version, which is slightly, well, for non-connective K-theory, where there's a similar statement which is slightly more general, where there's a, that is not surjective on pi naught. Well, I don't know, but not because of, I don't know, but well, slightly more general. So you, in applications, this is not really what happens often. What happens is that this is true up to idempotent completion. Okay. In other words, this is just a full subcategory, not necessarily closed under right factors, and this is not necessarily, and the quotient from this by that is not necessarily equal to that, but just cofinal in there. That's a slightly more general version, and that's what actually appears in localization theorems for projective modules in general, unless you're regular, where this is surjective. For the spectrum that I've defined, but this is the analog of connective K-theory. Remember that, and that only connective K-theory one is it needs to be surjective. Okay, Now we're going to do the analog of non-connective K-theory. And yeah. And one way of defining it is sort of, so I call this Karubi, the Grothendieck spectrum. So without taking care of the multiplicative structure, so when I talk about non-connective stuff, like non-connective K-theory or the analog for Hermitian K-theory, I put a boldface G. Okay, so I don't know if you can see that. So it's going to be essentially the colimit of a GW, then there's an omega GW. So something is called this is an algebraic suspension. Since we talk about the G category, so it's a suspension ring, completely classical Wagner Karubi, old in the 70s. You just take the tensor product with your DG category, it's a new DG category, and then you, you eliminate and complete, you take a pre-tangent or something like that. So that's what it is. So it's very easy to construct. And then you consider, you can go on, and so on, and that's what this is. Okay? And so, and this has, well, the same properties. So yeah, so I mean, this invariant under derived equivalences has a localization property, which now is this theorem with a relaxed hypothesis for this new spectrum, but where the sequence only exact up to factors. Exact up to factors. And so on pi naught, even for K theory, you will not get a surjection here. And for instance, GW, now A cross A up, is indeed non-connective K-theory. Okay? So that means this is the analog of non-connective K-theory. And that's what you need to use if you want actual localization sequences to be correct, also negative degree, unless you have negative K groups and stuff like that. So the effect, let me write down. So now if you want to know what is the effect, so there's a canonical map. So there's a canonical map actually to the homotopy fixed points, and this is homotopy Cartesian. So that means if you know your cofinality theorem here, what all of that means, it tells you what it does. So for instance, in positive degrees, it's an isomorphism. In degree 0, it's, well, if this is still an isomorphism in degree 0, then this is still an isomorphism in degree 0. And for negative, we know what a cofiber is like. Okay, so what else? So let me, so you get lots and lots of results, computations of GW. If you know what it means, Niesnevich descent, Wazowski's descent we already have, I explained yesterday. Projective bundle formulas, you can compute Grothendieck groups, high Grothendieck groups for quadratics. I mean, all of these, you can write down a blow-up formula for blow-ups along regularly embedded centers and all of these things. But now you take any theorem that's from K-theory that you can prove using derived category methods, and then you see what happens here, and then you get a result out. Essentially, yeah, anything, any K-theory result has an analog now, at least when 2 is invertible in the ground ring, because you can use all these derived category methods and these localization sequences and stuff. So maybe, so let me finish maybe with the Bus fundamental theorem, because you asked about it. So-called Bus fundamental theorem, which is like in K-theory. However, so now this, I really need to use sort of the analog of non-connective K-theory version. But remember, it doesn't change the higher homotopy groups, not even degree 0. It only changes negative stuff, right? So, yeah, I mean, let me write it just for rings, but it's also true for schemes and yeah. So this is degree n, say, and here, oh, let me say, we have 2 indices, I and upper n. Okay, so this maps into the polynomial ring. So but the duality, so L can be a ring with duality, but the duality on T is trivial. Okay. So 2 copies of that, which you may write as -1 if you want. It's just another copy of the polynomial ring. Then you get into the Laurent polynomial ring. T -1. Again, the duality is that's T fixed, okay, in this theorem. And now, yes, then the next term is GW, but now you go down in both indices. This is a split exact sequence. So again, I mean, this uses that. There's a split exact sequence. And so, and this is all for these, analog for non-connective K-theory. Yeah, we can do that too, yeah. Okay, now you can do both. Then you don't get a shift here. Well, it's a complex and it's contractible. Can I say that? Okay, so I think my time's up, so I should stop. Let me see if I understand the question. Yeah. So you have GW just for a ring, you said. Yes. Yeah. So we.
I was thrown off by this tensor with this shifts.
That's right. Well, it gives you the correct version of the loop. So. Well, I mean, of course, there's various ways of getting. I mean, if you just take with the definition, I mean, if you have this symmetric, the category of in a product space, this is a symmetric model category. You have a infinite loop space associated to that which has negative homotic groups trivial, right? Yeah. But for all these localization theorems, it's important to have non-trivial homotopy groups, and to have good control over the multiplicative structure, you want to have something. That you can write down, and what I wrote down is we have swell under for multiplication.
So there is this nice theorem by Ricard that if you only care about derived categories of rings and K-theory of rings, then like if you just have an equivalence of derived categories, you can actually give it Can you do anything like this in the duality setting?
I have not considered the question. Yeah, I mean, I think for the purpose of computing K groups or GW groups, I don't think that is very helpful. But I mean, I've never used that theorem for K theory, for instance. But